Hello, I am Tugdual Grall. I'm working as a technical evangelist at Mapar. And Mapar built a big data platform, a converged data platform where you can run batch operational streaming application. It's one of the platforms that I will use today for the demonstration. And the goal of the presentation today is to show how you can use big data and how big data is used in the context of racing cars. And it has been done in a context of working with a racing team and show how you can deal with data and why do they need with data today. And because it's going fast, and data has to go fast also. So why and what's the point of doing data in motorsport will be the first part. Then I'll show you a demonstration discussing about the architecture you can put together to build a streaming-based architecture to store, process, and deal with data and store the data. And discuss about what could be the next step for the demonstration on the type of application you want to build. So when you look at a race car or a race event, you see this team with many, many screens, many data coming all the time during the race. So they are looking at data all the time. And if you look at the engineers, they have 2 or 3 screens to look during the race. And you can also imagine that they're doing the same during all the tests and doing that also at the factory when they are only building or testing the car, the engines, and many components of a racing car. For example, you can see some information here that are generated by the cars during when they are racing. You will see at the top the red line, the RPM of the engine. The blue line will be the speed, and some acceleration on the side. So the G's of the car will be the green, the gear position, the throttle, and also how they use the brake. And it is used to understand where and when during the race the driver is changing something in the car. And this is used, for example, to define a strategy. Here you look at the strategy of different options on the weight of the car, comparing two options. When do they stop the car to change the tires, to add more gas, and so on, and analyze the time that they lose or win during the race. So it's also a very interesting set of data that you can use when you want capture data, store them, analyze to understand how the tires, the behavior of the tires or the engine, do some predictive, understand or guess what will be the behavior of the car depending of the time and depending of the data you get in. So this will involve and help the team to build a strategy, to choose when to stop for a pit, but also keep all information to understand over a season, on multiple seasons, on multiple cars, multiple drivers, how the car behave, and over time be able to build some very smart analysis of the data, very smart maybe machine learning about to understand what will be the behavior for the next race, guess what will happen on how we choose to deploy a new component or change some adjustment on the car. And when we talk about data, it's always interesting to get some sample. So if you look at a car, they have up to 300 sensors on the racing car. You saw some of them on the engine, the RPM, the speed, the brake, the throttle, the G's, but you also have a sensor for each wheels, each brake, each tires, and many, many information. And this specific sensor will send the data to the pit all the time on multiple channels. It has to send the data very, very, very quickly. So you have many channels because you want to send the data in less than 2 milliseconds. On a specific network also, because during a racetrack, on a racetrack, you can lose the connection. So he has to send the data to the paddock all the time, as fast as possible. And if you look for a car, it will be 1.5 billion data points that will be sent during a race. all the time, all the time, all the time. And 5 billion for a full race, for a specific car. For 90 minutes, this means it's around 5 to 6 gigabytes of data that is generated by one car. So the goal is to be able to capture this information. So the sensor itself, it's not where I work. But when the data is sent to the system, how do you take it, store it, process it? And if you look globally on a weekend, on a racetrack weekend, and it's some data that I saw in 2014, we can expect to have more information today. It's 240 terabytes of data. And every information in this case, it's very interesting to keep, because you want, as I said, do some analysis after the fact, for example. So how can you build an architecture from a data, from a software point of view, that can deal with that? And the most important part, he has to deal that in real time. Because getting the 200 gigabyte or terabyte, move them to a big server or big cluster, it's easy. But what you want to do is to be able to capture that on the fly. So the network that you have on the track and on the cars is you have a specific network, kind of an aggregator for all the data that is built and managed by either the association of drivers or the Formula One team. And then he will kind of route the different messages in different parts. And today, most of the systems that are in production on the racetrack are custom built using, most of the time, custom network, custom protocol written in C and C++. And people start in the racing car teams to look at moving to something that is more standard, more open. And some of the components that I will talk to are what they are looking at today. So the goal is to be able to send information for real-time analytics, store information to send to a specific engineer's workstation in the paddock or back at the factory, be able to also synchronize the data as quick as possible. On what we are looking now, it's also, instead of storing everything on the paddock and then wait that the team is back to the factory, find a way to send the data over the wire almost in real time from the Grand Prix in France or in Brazil directly to the factory in UK or in Germany using the same network, using the same network protocol on the same API to simplify the development, to open the integration. So, as you can guess, I was not able to bring a Formula One here. So what I built a small demonstration with some friends. On what we use a race car simulator. We use a streaming technology that I will explain in detail to capture messages and send messages. And then you build an application to consume these different messages, to do real-time analytics, and do some offloading or for the back office analytics, and build more stuff at the top of that. So, for example, what we use, it's Torx. Torx is an open source race car simulator. It's from 2007 or 8 or something like that, built in C and C++, available on SourceForge, as you can see. And it could be used as a game. I didn't test it, but it could be used more importantly as a simulator that automatically generate race and generate cars and behavior on a specific track. And it's used quite a lot by people that want to understand physics and simulate physics for racing cars, like speed, Gs, and so on. So this is what has been built, what has been used for this demonstration. So let's go to the demo, and then I will explain to you the architecture behind it, showing some little bit of code, and discussing what could be done now that we have the product. So here I have the simulator. I have also a dashboard purely based in HTML, JavaScript to do some charts in real time. So in Torx, you can choose the type of track, the type of cars that you want to use, how many cars, on how many laps and so on you want to use during a race. But I will just use this by default, and I will start a new race. So the simulator will just generate some data, generate some cars that should sound. This is where I'm starting to be worried. Should some data that I don't see in to my browser. Okay, good. And so it's storing data, sending data into the system should be visible. Network issue, I guess. But also, let's talk about the architecture then, and I will come back in a minute. We have two parts in this system. One is for the real-time analytics that I was not able to show you, that receive messages and show them. So the different events to show the RPM, the speed in real time. And another part will store the information inside the database. And because it's stored inside the database, you can start to do some analytics. So before going into this demonstration of the analytics, the product on this demonstration is built on various components. The simulator push or publish messages generated by the application to a stream, on a topic, using the Kafka API. And then you have two consumers, so two services that consume the messages. One that failed, and the other one that saves the data into a database. And in this case, the database that I use is MapperDB.json. It's a document database that is part of the cluster, and allowing people to query with different languages. One of them, and it's quite important to realize that even if we store data in many different storage, in many new databases, NoSQL and so on, one of the most common language used still for analytics is SQL. And it's not only because SQL is a powerful language, but it's also because most of the tools that people are using today talk about ODBC and GDBC, connect to a SQL engine using SAS, Tableau, ClickView, and many, many other technologies. So this is why, for example, in this demonstration, I choose to address and use the NoSQL database to do queries using SQL. And the project that I use for that, it's an open source project in Apache. It's Apache Drill. And the query that I use is, if we look at some simple record inside the database, I will do a select star with a limit going into a table that is called all cars, all the event that has been generated for a car, for all cars. And the format stored is JSON, so it will automatically recognize the schema out of the different fields. And the way it's organized, it's exactly the way the sensors inside Torx send the data. In this case, you have the race, the car ID, and a set of sensors as a batch, as a buffered set of information. And then you can do more advanced queries using the SQL and JSON features of Drill. Obviously, you can transform the JSON messages doing your any type of big data API and so on, but you can directly work with the data using this way. And an interesting part also is I have another set of data, very basic, that contain inside a JSON file on my distributed file system. This contains in a JSON file the list of cars, the model, and the driver. And the challenge here is, suppose you have many information about the car, the engine, the sensors, is you can, using SQL, do join between a NoSQL database, a JSON file, a Parquet file that you use to optimize for formatting, for storing data on the distributed file system. Here it's a pure, very basic text file. So my main query for this demonstration is just a join between a NoSQL database, a NoSQL table that contains many rows, and a simple JSON file that contains few rows. So if you look at the inner join, it will be the main table query on all cars. And I use a specific function that comes with SQL in Drill that is called flatten, and will explode the different rows that you have into single rows or single documents. Like that, after that, I can do group by, aggregations, calculations, and so on. This is what is done here. A group by cars, model, and driver, and I just calculate the average speed. If I submit the job, I have for each car the average speed for all the races in meters per second and kilometers per hour. So this is one way of working with the data. And when we talk about big data, we may have 200 terabytes of data. The way it will work in this case, you have to think about how do you store the information and how do you work with the data. And this is one of the most important parts when we talk about big data globally, but also when we talk about real time and how you want to modify and access the information. Most of the time, when we talk about big data and storing the data, you have two options. And usually you will use a little bit of both. In one case, you will store simple files on a distributed file system that give you high availability and, more importantly, scalability. You can add more and more nodes. So for example, when you do Hadoop, you will use HDFS or Mapper file system, and you can find other appliances, for example, that will do that. The key point in this case is to choose a proper format that can make it very efficient to write or to read, depending on what you want to do with the data. And if you need to access a subset of the data, if you need to modify data quite often, you will use a database for the same reason you use a relational database in your application. But because on big data, you want to keep lot of information. So meaning you will have to be able to store a lot of data, so scale out to add more and more storage as you have more and more data. But also, even if you don't have a lot of data, if you keep data for a long time, the formats that you use, the schemas that you will be using, will evolve over time. So one of the main reasons also to use a NoSQL engine in this case, is to take benefits of the flexible schema. If you think about what we are doing in automotive in this case, or racing cars, is the sensors that you have in 2014, 2015, 17, for example, could change. We have more and more information. So to be able to store the information easily and continue to query and process it, take a format, take a database on the file format that you can quickly add new attributes to be able to leverage a new feature of your applications, the new features of your sensors. Don't try to put this kind of information in a relational database. But you see from the demonstration, we can use a SQL engine, so a relational engine, to query that. And many other things, obviously, to query. So one of the other challenges when you talk about data in real time, it's how do you stream the data inside the system. And I talk a little bit about Kafka, using Kafka as an API. And what you have to look at it's how many messages, how many events you will manipulate. Moving millions of events for hours, minutes, or seconds, depending on your business. In this case, the number of messages is huge, but very small. If you look at a website, on the clicks could be millions of messages per second or per minute. How big is your system? You want to capture that, be able to send that on your network, on your application. This is why Kafka has been built. So what I use is I use a Kafka API in this demonstration. So if you don't know Kafka, this quick, very, very quick introduction has been built. It has been built by people at LinkedIn, and they created a company since, and implemented in Java, on Scala mostly. And the goal is to have a distributed messaging system that can scale easily. And the important part, because based on the way it's implemented, it's distributed messaging, easy to scale. exactly for the same reason. When you have a NoSQL database, they have some of them have been built from day one to be distributed and scalable. So the way it has been done is like any messaging system. You have producer and consumers, and in the middle you have a broker, a system that captures and stores the messages on which consumer will get the event from. But the way it has been done into Kafka about scalability, it's for each topic on which you push messages, you may have multiple partitions. And each partition will be physically stored if you have multiple servers on different physical servers. And this is an important part to understand is when you create a topic, for example, all cars, you will say, I want to use 5, 10 partitions. You will put 5 or 10 physical machines in parallel. And the producer, based on a key, based on a random key or what you want to use, for example, it could be the car, in this case, the car ID, will choose a partition and go on a specific part of your cluster. And if you need more scalability to the right, you will just add new producer or add new servers to scale out. The challenge here is, and this is very important, the most important part to understand about Kafka on partition, the order is guaranteed by the system, but only by partition. So for example, if you have in partition 0, you have car 0, in partition 2, you have car 2, you just be sure that the order of the messages received for car 1, car 0 and car 2 will be good, but you cannot compare, or you cannot be sure that the message will between car 2 and car 0 will be sent and received in the same order. And it's also due to the fact the way the consumers are working. For the same reason, if you want to scale, you want to divide, you want to add more servers to consume the information. So you can run as many consumers as you want. And you have the concept of consumer groups. That will be for a specific service, for a specific consumer. You have multiple processes running on different machines. So you have a group of consumers, most of the time running on different machines if you want to scale. And each consumer will read a specific partition. On a partition, it's only read by a single consumer to guarantee the specific order. And Kafka will deal with failover on all this when needed. So as mentioned, the way Kafka has been built, it has been built from day one to scale out. And you can distribute the system because every time you will store messages in the Kafka cluster, it will be on different machines. So if you look at the architecture a little more in detail, producer will produce message and send them to the cluster. A Kafka cluster is a set of multiple brokers. In this time, I have 3 brokers that are managed in terms of availability by Zookeeper. And in this case, the consumer will automatically read some partitions, and they will be divided to create new applications and add new services. Mapper streams is using the Apache Kafka API is just like the fact internally, where the messages are stored, it's different from Kafka. Kafka is usually one server that contains and will write on a single disk. Mapper streams will use the mapper cluster that is already distributed, that already write on many, many disks. So the replication, the distribution of the partition, it's not done by Kafka itself, it's done by the mapper cluster. But from a developer, it's exactly the same API. You don't have to change the API, you just change the configuration and the way you address the topic, because you don't have a specific cluster to connect to. So what happens is when you want to produce a message, you will just write a new producer record. This is a basic 0.9 API. And if you do Kafka today, you see the name of the topic. It's specific here. It's because you don't have a specific broker, and you can have millions of topics inside Mapper. What we have done, we have a namespace that is called a stream, on which you have multiple topics. This is the first part, /apps/pacing/streams. This is just a namespace on which you will write into the sensor data topic. And then you post a message and you deal with exceptions and so on, depending on what you want to do. And when you consume the message, it's the same. It uses pure Kafka API. So in this case, you can really start to build any type of application that push data in and consume. If, for example, I look at the code in my application, in this case, this is a consumer that receives information on the message is sent as a JSON, and I just insert the different messages in the NoSQL database. Keep the message safe. And one of the important parts is don't put code into your consumer and your producer. Just formatting code on this kind of very basic operation, storing on this or transformation. But if you have long processing to do, use other frameworks like Spark Streaming, Flink, and I will go in detail in a minute, that are made to process data on the fly. And for the post, it's more or less the same. Get the topic and send the message. So everything is available on GitHub. So on this application, we have done two basic stuff: UI, database. But the important part about streaming and starting to think about the data first, the streaming data first, is you can make a lot of evolution on the fly or add new services. So for example, in this case, I was talking about data that you store. Each message will contain a buffer of sensor data. And this sensor data in this specific release contains only three information: the speed, the distance, and the RPM. Quickly, without changing anything in the global architecture, just changing, for example, the sensor or the code that simulates the sensors, you can capture more data. And this is one of the one of the things you can do immediately with torques. For example, you can capture throttle and gears, current gears and throttle. And if you look in real life, you will have many information. I was talking about 300 sensors for a car, so you will use this to send messages. And an important part is for 300 sensors with millions of messages, you will probably not use JSON. This is very good to use JSON for showing on slide. In reality, the cars use binary format, compressed, and send that over the network. And then the first part will be to deserialize that into something you can use in your processes. But for a debug and for a demo point of view, it's very nice to be able to use it using JSON. Also, based on what we have into torques, we don't have a lot of sensors. We don't have these 300 sensors, like one by tires or brakes and so on. But in reality, you will add more and more information, more and more sensors. So if you find an open source framework that have more, an open source simulator that have more information, I will be very interested to know about. But the main point, and this is one of the main reasons the people were talking about moving to a new architecture based on streaming and based on Kafka-like or Kafka, it's to be able to add quickly new services inside the application. And to be able to do that, you have to choose different framework. And the goal, for example, will be, I want to add a new services. And Kafka is used for streaming data, moving data only. Then you talk about stream processing, and you have different things, streaming data and processing the data. And for example, it could be to calculate something on the fly, do alert systems, doing some alerts. If the engine and the speed of the cars are not between these different two values, do something. Or if I want to calculate the average speed for the car for the last n seconds and so on, print it. And the goal is to be able to, without changing anything in the existing application, just consume the messages in a different way. And this is a very important part in the way you build application today, by adding new services on existing infrastructure and existing architecture. One of them, at least when we talk about big data or data processing, will be Spark. Spark is a distributed computing framework that allow people to develop processing using streaming, doing interactive analytics, and a very powerful framework that you can deploy on many nodes. And it uses the same concept, at least when you develop, that people used for when they do MapReduce. It's the same kind of approach to the data. But instead of using like Apache MapReduce that was built inside Hadoop to do batch job, it's made to do batch also. But it has been done to run a lot faster, allowing people to do streaming and process the streaming on the fly, process the stream on the fly, and do interactive analytics. And one interesting part about Spark in this case, for people that I used in the past Hadoop, is you can run on a single tool, Spark, real-time on batch. ETL job kind of, on SQL job kind of analytics. So the benefits for the developer, it's a single technology to learn, to kind of manage many type of job he has to do with the data. And you can use the same tools as the data engineers, transforming the data, enriching the data, but also as a data scientist. So having the same tools for different parts of the team, it's quite interesting. Another framework about streaming and processing, it's Apache Flink, that allow you to register and subscribe and produce messages the same way you do it with Spark, with a different way of handling the streaming. Internally, they don't use the same architecture, especially regarding streaming, but you will be able to do streaming dataset API to manipulate the information. So more or less the same. Using Flink, you will be able to do real-time and batch-oriented job, depending on what you want to do. And it runs also in memory to be very efficient and fast. One of the main differences is the way the stream is handled between between Spark and Flink. In Spark, they do internally what you call micro-batching. So small amount of messages are sent by a batch, and then you have in your code, if you want to do complex functions between windowing on time and so on, it adds some complexity. Where Flink is just streaming the data all the time, and you choose the way you want to deal with the event. So it makes it easier to deal with the stream and do complex event processing, so CEP if you need it. React immediately to an event based on specific rules. So what I have done here is use, and I hope this time will work, I use the same messages, the same application, but I want to use that to calculate, use Flink, the average speed of the cars for the last 10 seconds or last n seconds. It's a basic example of what could be done with streaming data. So we'll run a new race. And we'll run my Flink application. So we see here for each car an average speed, and it should refresh every 10 seconds. So the way it's built is the system received here from the Kafka API a JSON message. And the data stream coming from the data stream of Flink connected to my cluster, my Kafka cluster, receive messages. And I just say, take this as a source, take this specific Kafka topic. And here in this case, I'm using mapper streams, but you can obviously use pure Kafka. And because I know it's a JSON message, I use the JSON deserializer that is available inside Flink. So depending on the format, you have multiple deserializer you can use. This is the first part to build a data set that you can start to manipulate to do some processing. So then on the stream, what I want from this JSON file, I want to get a list of keys, a list of tuple, a map of, for example, the car, the speed, and how many times the speed has been captured. So I created a flat map function for Flink for this specific message. So if you see here, I just get the car ID from the message. And I get the speed from a sub-element into, if you see, the message as this structure. So sensors.speed, and in this case, the race ID, the car ID is here. So I just first create a tuple that I will be able to use to do other operation on my stream processing. So the next step, I just want to group them by the first a key that will be my first field, the car ID in this time, and then on a specific time window. And in this case, I'm not using any of the timestamps that I have inside my messages. It's one option. You can say, look at the messages, use the timestamp to manipulate and process the data. In this case, it's just look at every 10 seconds you receive messages, do this. And what he is doing is reducing to extract and count for each message, add the speed and add the count, the number of data you have into this specific car. So it's done by car. And then I will just do a very basic average, a very basic function. And the last part is I want to transform a little bit the format of the message, because internally, if I look how it's done internally, if I remove the last stage, and I rerun my consumer, because in this case, Flink is just a simple consumer for my application. To be sure the race is still running. No, it's not running. So in this case, Flink will only consume new messages coming from the system. And I will come back in using the log differently into the application. So internally, the data are stored with a key and different value. This is what I'm doing at the end when I do the format that I use to do the print or the transformation. I have a tuple that contains different information, like for example, in this case, the car ID and the average speed, and I just want to format it differently. And just because in this case, what I want is to drop this message inside my console. So using a simple step-by-step flow for my streams, I can capture the information, transform the information, do some aggregation, depending on the level of data that I want to manipulate. And in this specific example, I only print that in the console. But the goal is to capture this and maybe send that to another stream, to another topic. For example, to send some information in real time to one of the engineers on the paddocks that needs to know if the cars, what's the average speed for the car at this specific location, is it good compared with what we have done in the last 40 laps, for example, and automatically give some information. We can also imagine to react directly and give some information to the cars, but it's forbidden. You are not allowed to modify the configuration automatically. But the point here is I can process data as they come. And this is an important part when we talk about data on big data. In reality, most of the big data you do, it's one event at a time. It's one event after one event after one event that will generate terabytes of information. And the goal of all this streaming-based architecture for capturing the data and processing the data is to be able to react immediately. And keep the store the data. And this is what I have done in the database. All my data are stored in my storage, but this specific service is totally an addition to the framework, an addition to the application, to be able to process and add some value to the system. So if we look at the application in the context of a Formula One and why it was built this way on the POC, it's people want to have an easy way to stream and process the data in real time in a scalable way. So you have two things that you have in this case, two or three things. Be able to store the information. And this is an important part when you start. Think about how big is your data set today, but more importantly, and this is a very important point, is how fast it will grow. If your data set is only 10 terabytes and it stays between 8 and 10, it's very easy to understand how you can organize the storage. But if it starts with 2 terabytes and you add 5 terabytes every day, you have to think totally differently about how you want to organize that in terms of data storage, physical servers, and so on. So think about distributed and scalable storage on the same way, because you want to be able to process information as fast as possible, distributed and scalable processing. Flink is distributed and can scale. Same for Spark, depending on what you like and the type of operation you want to do. And for the capturing the data, it's the same. The reason why we use Kafka on MapperStreams here is you can add as many producer and consumer as you want. One of the tests we do is testing with 8 million messages per second, or small messages, but just to be sure it can scale, fail over automatically. One of the also part, as soon as you are distributed, it's easier to work with failure, as soon as the system is built for that. This is the case of Spark, of Flink, of Kafka and MapperStreams, the NoSQL database, and the distributed file system, based on commodity hardware that you can use. And it's an important point here when I talk about commodity hardware, especially for this use case. Commodity hardware doesn't mean that you can keep one of your old servers you didn't use for 5 years and do big data on it. It depends on what you want to do with it. If it's only storing data, yes, you can. If it's just very old data that you will keep for years. But if it's about processing the data and capturing the data in real time, Kafka, MapperStreams, Flink, on Spark, usually you will size the data, you will size the server, so it's based on what you want to process. You can see in the big startups, they have, for example, Spark cluster that have 100 terabytes of data, on the terabyte of memory on the cloud, because they want performance. In this case, you scale and you define your servers based on the use case. And the key point is to be sure that you can leverage, if you have a good server, leverage hardware, the CPU, and all the disks you put in it. And commodity hardware in this case means you have the choice in terms of configuration, vendors, the configuration of your server, disk, type of vendors you want to use, and the type of OS, any Linux, for example. This is what we call commodity hardware. It's not take an old server and put that in production. And in terms of architectures, what we see more and more, and especially with this use case, is the key part is streaming data first. You know, as part of the application, we talk about mobile first, for example, application. In the data world, we start to talk about streaming first. Think about how do you want to capture the information. Try to do that in real time. Use change data capture system to listen to any event inside your database. One of the things they have in the POC we have worked with is they use SQL Server. So we use a change data capture event directly from the relational database to capture some of the event. So you don't change the architecture, you have a new event coming inside your system, and you can build new services. On the good part, you decouple completely the source of the event from the target. So if today the first step of your application is to use one of the change data capture feature of your relational database to send event in real time, and you add some code to process that, and tomorrow you are moving from this relational database to something else, you don't have to change anything inside your application except this specific source. Think about what you do when you talk about microservices. It's exactly the same. You have specific set of services here communicating with many other services using event completely decoupled. Same approach. Adding more and more use case to the system. And the key part here for me is this is not only about Formula One. Formula One is one use case where we have been working to help define a new architecture. And we can stay in automotive. Automotive is working the same. The connected car in the future, we have POC working on different companies. They use the same approach. And in this case, cars are not, they don't have 300 sensors. They have few sensors sending few amount of data, but you will have millions of cars that are connected. So the challenge will be exactly the same. How do you capture, how do you store the data if you want to keep more and more information? Same for telcos. Telcos, I'm working on a project where we have between 2 or 3 terabytes every day. It's all the event happening inside the network. You want to monitor that, store information to be able to do some prediction on the failure on the network, understand immediately what's the impact if you have a specific part of your network that is dead. And you do that as the data are coming inside your system. And one of the information could be your video player at home start to be slow and buffering information. You want to immediately understand what's the problem, from where the problem is coming from. So stream the data back into your processing on smart kind of application. Finance is also easy in the sense that, when I say easy, as a use case to understand. The main use case, very easy to understand, where you need streaming data in real time and add value. And it has been done for many years, but now you see more and more financial institutions using the same architecture, like Kafka, Spark, or Flink, is the fraud detection. You use your credit card, you are on a point of sale, you have few seconds to take the message, send it to your backend, analyze, process, send back if you accept the payment or not. And even now you have some credit cards, of any moment, any amount, they will always send a message to the system. So it's, again, potentially millions of messages every second. Obviously, not on a single data center, not on a single server. Think about scalability again. Many other use cases like ad management or content. When I say content, it's, for example, on retail will be recommendation of content, recommendation of product on a website. Moving to real time, moving to streaming the data. It's one of the most of the biggest tasks we see today with information around data. We don't do batch anymore, at least on new project. On old project, it's moving from batch to streaming, using different technologies that are used. So I will take a few questions, but if you want some information, so first you have all the source of this demonstration. I hope you will be more lucky than me to have the first part of the demonstration working. So you have the Torx plus the Java application. I will check in the Flink application just today. We have a free ebook about streaming architecture, thinking about how you can start with streaming and type of application you can build. Free online training, and I have few gift or giveaway if you want after the talk. So if you have any question, yeah.
Thank you for that. My question is, maybe if you come back to the architecture.
Yeah.
Can you repeat the question?
Yeah, no question. For now, the question was only, can you go back to the architecture slide?
Then your consumer here is fine. There is no Flink for
No.
consumer is your Java consumer
Yes.
only, and it works very well.
Yes. But one of them didn't work very well.
Okay, because you have no compute operation to
Yeah.
do, no cleaning
No.
operation. The data are well cleaned and there is no compute operation to do.
In this specific example,
In your case. Okay.
usually what you see, so the question is, in the consumer that you have here, you don't have any compute. So the answer is yes, in here.
Okay.
I have two consumers here.
Okay, and there is no latency in your system. I mean, how to deal with latency problem? I mean, data who arrive.
So how do you deal with latency? And the latency will be, you have different ways, so it depends where it's coming from. If you start to have latency, you have back pressures that you want to put inside your application. If it's a code yourself, you have to deal with it. And it will depend a lot of which framework or not you are using. For example,
The problem is the timestamp. I mean, you will print it on the dash on the graph, and if your point is late, how do you replace it in the?
in this case, we don't. We just because the time it's time, we don't use the timestamp of the message when the message is received, but the timestamp that has been when it has been emitted in this case.
Okay, then that means that you print your point by,
Yeah.
by minute, for example,
Yeah.
or by second.
Yeah.
By minute.
No, in this case it's by seconds, but I don't have a lot of messages. And what you do in case of scale, if you start to have issue with latency, you have to add more servers if you
Yes,
can.
because back pressure is efficient with
A subset of the data.
with a window that
Yeah.
is more than 1 second.
Yes.
Back pressure will not work for a point
For-
that we will print by second.
Yes.
That's a problem. That means that in your case you allow to lose data that is.
So no, we don't lose any data. In this case, you won't lose any data.
No, you don't lose.
In the chart, you may
Yes.
lose data. Yes.
the chart,
Yes.
You allow this.
Yes.
Okay.
Yes.
Suppose you have a batch-oriented system and that today you want to move to real time, but you are not sure whether you want to do it in micro batch of 10 seconds or 20 seconds. Today you might have it do it in every day once, and then tomorrow later on you have new services that you want to add, which you want to process it every 15 minutes or something. How do you choose then the framework like Apache Spark or Flink?
So the question is, today you have an existing system that processes your data that is batch oriented, and you want to move to streaming. How do you choose the time window or the micro batch?
Because today's requirement can be like you are processing every day, but then tomorrow it can.
So when you say I want to do it every 15 minutes or every hours, for me it's not micro batching. You don't stream. Just it's easier to start a new job in this case. So you still do it in batch, but smaller batch. After one of the reasons I put Flink, it's because it's easier to manage. You don't have, because it's not, in this case, it's not a batch, micro batch. It's just because I wanted to choose that data is moving kind of away. The micro batch in Spark is just based on what you have to do with the data, on how complex will be to deploy and deal with the size of your data you have in memory. Spark is changing. So one of the big improvement in Spark coming now, from now to the next, it's typically to kind of avoid this micro-batching API that make complex the processing of the data. Maybe internally we'll continue to work the same way, but from a developer point of view, it will be easier to manage. So the answer is you have to test. And what is key in this case is just to be sure that your business logic is not too dependent on the time window. Because if you have to say, for example, you cannot do in Spark streaming, do something in less than 50 milliseconds. This does not exist. This is why we talk about micro-batching. So if in this case, you have to find another way to deal with the data. Even with Spark, with Flink, I don't know in my use case, I've never had to go down to this specific level. Yes?
Another question maybe about the design.
Yeah.
Then you have a consumer, okay, from Kafka, and there is another solution maybe that is missing in this presentation is Elasticsearch also and Kibana. Did you test this solution?
So the question is, here I'm using a consumer that do a chart. And your comment, was you have another solution with Kibana on Elastic. Yes.
You have no compute operation, nothing.
Yes, but
data set from point
it's typically what will be very easy to do here. It's either to directly use Logstash to get the message to Elastic, or use the Flink to Elastic sync. Yes, it's possible, and I should have done that. It will work. The graph will work. But it's just, for example, internally on our platform. When you monitor the cluster, what we use for analytics in this case, we use Kibana internally with the same approach. We use FreeND, but it's not we could have used Kafka in this case. So, but the very good point here on your question is, as soon as you put message on a topic, the way you consume is as you want. And this is typically why it's very important for me to think about streaming, emitting event, because after you have a lot of freedom. And this is what you have, I think, for me, it's understand storage, distributed storage, understand a distributed messaging system. If you need, it's again, if you need reliability and scalability, if you have we have 2 messages every minute, you don't need it. You can, but you don't need it. And understand a distributed processing layer like Spark or Flink. And same, I think, a SQL engine like Apache Drill, it's quite important if you do data-centric application. I've worked 9 years for Oracle a long time ago. I do more SQL today than I was doing at Oracle, because you always start this way.
Did you consider Storm and
Storm and I don't know Esper. So did I consider Storm? No, because I don't need it. I will use Flink to do the work if I have to do it today, or Spark.
But Apache Flink, for example, does it guarantee at least once processing of
No.
the event? No. So how
You have to put that in the way of at least one. Yes, at least one, not only one.
otherwise you cannot use it for financial applications.
Yeah. You have different ways of doing it, but you know in which offset you are in the message, so you know if the message has already been dealt, or you can add some codes to that.
And today, what do you think about the new API of streaming of Spark? I mean, before the new API, I think Flink is more suitable for some kind of because this stream was micro batch and it works, but the API was not very good. I mean, you have a nightmare in 3 level to go to the data set of Spark. And now I think they modify the API and it is more written than.
So the question, if you didn't hear, is what do
you think about the new API?
As I said, Stream is updating the streaming API. What do you think today about the streaming API of Spark? Until you have the new release, for me, if your system is purely streaming based, Flink will be easier to use. That doesn't mean Spark doesn't work. But if you focus on streaming, today I'm sure the thing is, it's very good that Spark is simplifying and making it easier to manage and develop. So as soon as it's easier, it's very good. And after, it's really about community adoptions. What do you think? What your skills are? Because from what you can do in most of the times, they are very similar. And it's also look at the skills in your team for this, for how do you choose a technology in this case. When they are equivalent,
Before it was very difficult to use this team.
this is why I use Flink for this demonstration.
Yes, but now with this new API, you can say that you can go also.
Yeah, but today on our customer in production, most of them are using Spark. Okay. They're using a Storm from I will say the legacy. I should not say that, but people that are starting new project, when they need streaming, they do Spark in most of the time. For very specific use case, when they really need today, with a supported platform, they will use Flink.
Do they use Spark or Scala? Or
It depends. The question is, do they use Spark or do you use Spark with Scala, Java, Python, and R? And once again, it depends on your team. What you will see is very often the data scientist part will do Python on R. The data engineers processing the data will do Java or Scala depending on the background. If you are my only comment on that, if you are getting very serious about Spark, and it's becoming your main processing layer, you should learn Spark. You should learn Scala. Yeah. If you do just small amount of processing and you don't have time and the resources to learn Scala, you can do Java, it works very well. But sometimes it's harder to write. It's not the same with Flink. Flink is Java first on Scala, where Spark is Scala first and Java in terms of usage. So thank you.